Hey, good morning to you all. Yeah, this is week 4, and typical of Wednesday's session is that there's nothing new to announce. Therefore, we can go on and start the topics today. So we'll try to wrap up chapter 2.1 where we talk about there's this mechanism called TLS now. Previously we call it SSL, right? But it's now all referred to as TLS. And today I'm going to tell you how TLS works. So in this video, there's going to be 2 parts. One is to quickly review how public key works. And then I will show with the public key crypto system how we pass a key, a secret, between a pair of hosts where there's no agreement on the keys they use yet. Okay, you see the trouble is this. Let me try to be clear again. On the internet, right, we have network applications where you have a receiver and a sender and they need to communicate. From time to time, we would really like this communication to be secure. And what we do typically is to encrypt the message we send, okay, to scramble the text we send such that if anyone intercepts the message, they won't be able to tell what the message meant. But you see, in order to encrypt or to hash the original text, the sender and the receiver needs to agree on using a key to do the encryption such that sender encrypt the message, send secret. Receiver receiving a secret, use the key to decrypt, and then the receiver will understand what the sender meant. But you see, the trouble is, hey, to do the encryption, you need sender and the receiver need to share a key. Okay, this is a traditional encryption system. But that means the sender needs to send the key to the receiver first in order to get the encryption system started. And hey, before you have encryption, sending a key, that's not secure. Yeah, so you have a serious problem here to ensure secure communication. So we use a public key system where the sender uses one key, receiver use another key. And yet, the sender used this key to encrypt, the receiver used this other key can decrypt, and they will understand each other. Okay, so this video, the first half is to tell the magic, and the second half is to tell with that magical asymmetric key or the public key system, how we establish a secure connection with TLS. Okay, so this video, almost 4 minutes, okay? Stay focused because it's something that's very basic nowadays, sending secure data over the internet. Next, let's explain how TLS works. Before that, let me go back to the very fundamental computer security. How do you encrypt a message such that it can be kept as a secret? So the classic approach is the secret key mechanism. So what we do there is to generate a key, and we share the key with Bob and Alice. So when Alice has a message to send, use that key K, apply the encryption function, and it's going to generate something that's messy. So a third party in the middle here might intercept the message, but without knowing the key, it's not able to decrypt it. Bob, on the other hand, receiving the messy message, using the key, can restore the original message. Okay, so this is the classic secret key communication. Unfortunately, the secret key system will not work to implement TLS. If you think about it, we have one shared secret key. Let's say if Alice is the one generating the secret key, Alice is yet to send the secret key to Bob, isn't it? I mean, then we need TLS because we fear we send password in clear text to the other end. So Alice here is sending the shared secret key in clear text to Bob. Same problem. Yeah, so we do have a bootstrap problem with the secret key. Now, to address that problem, we use this other system on top of secret key. It's called the public key system. So instead of using one shared key, public key system generates a key pair. One is called the private key, the other is called the public key. All right, so the receiver of the secret message is over here. Sender of the secret message is on the other side. What the sender does is to plug the message she wants to send and then encrypt it with the receiver's public key. Yeah, the reason that it's called the public key is exactly because R is going to give out that key to the public, including the sender here. So this is going to scramble the origin. So this function is essentially scrambling the original bits here using this particular parameter. So the encrypted message, as it arrives at the receiver there, then apply the same function and take the received message, and receiver can decrypt with the other key in the key pair. So this is going to give the original message back. Now, the private key is the one kept by the receiver, and no one else in the world will know. Therefore, you ensure that no one else will be able to decrypt the encrypted message. So only the receiver can see the original message. So this is how the public key ensure secret exchange. So TLS illustrated up here works this way. Alice here is a client requesting service from Bob here, a server. So client here first sends hello message to the server. Server in response sends server's public key. So Alice here can then encrypt the shared secret that has been generated before using Bob's public key. So Bob's public key here. Then encrypted master key will arrive at the Bob side. And because Bob is the only one holding the Bob's private key, therefore Bob can restore the master key from EMS. And that's how Bob and Alice establishes the shared secret key. So in this case, you see Alice is the one generating the secret key. And from then on, all the messages are encrypted using the master secret key. And that's how TLS worked. All right. And by the way, this public key system there, the inventor, 3 professors, they eventually won the Turing Award, which is the equivalent of Nobel Prize for the computer scientists, because it's really powerful when it comes to ensure secure communication that involves multiple parties. All right, great, Henderson. Thank you for the feedback. Yeah. So I just ask on the live chat whether you guys have heard or learned about public key system before coming to the lecture today. Okay, some said I've heard about it but never really learned about it formally. Yes. Yeah, I guess many of you heard about it, and some of you might have learned about it. Not so much. Yeah, it's very often used, and RSA is one of the older ones. There are nowadays more higher complexity public key, such that it's harder for the hackers to find a hack to decrypt. I'm in cryptography grad class right now, so we learn all about it. I see, Hassan. Good for you. Yeah, so usually there's quite a bit of math behind such a system or any cryptographical system, because it's a science about scrambling numbers. Because nowadays in the digital world, materials, content, information are all encoded in 0 and 1s, essentially numbers. Okay? And making sure that the numbers you send out are secret is scrambling these numbers, rearranging these numbers, such that it's meaningful originally and hopefully becoming not so meaningful, so the interceptors don't understand. Okay. Yeah, good. Yeah, okay. Yeah, so you see that it's magical. Very useful nowadays. All right. And you know why? You know what, guys? This is the end of 2.1. Starting from this point on, we are going to go over those important applications we see on the internet today. Starting from web browsing, next email, next DNS, and then a P2P application. So the rest of today is going to be all about web browsing and the application layer protocol supporting web browsing. That is called HTTP. So in this video, a little bit long, almost 6 minutes, Polly is going to introduce web browsing, or hey, review quickly what web browsing is, and then start introducing the protocol HTTP. It is surprisingly straightforward. Web and HTTP. Let's do a quick review. Web is essentially a bunch of these web pages interconnected. So each web page consists of a number of objects. The base object is typically a HTML file. And then in each file embedded are several referenced objects. And these objects could be another HTML file, could be a JPEG image, could be an applet or a script or an audio file. Each object on the internet, on the web, is addressed by the URL. So this is an example of the URL. There are three parts: the host name, and the path, and the file name. Okay. And the HTTP protocol there to support the web application runs in the client-server model. So the client here are essentially the browsers. The browsers is essentially requesting for web objects and then in turn receiving web objects, of course, using the HTTP protocol. Now, another task the browser does is displaying the web objects. Just to clarify, passing of these messages and web object is the HTTP protocol's job, but displaying web object is actually something else's job. It's the HTML interpreter's job. Yeah, so HTML interpreter is not quite the HTTP protocol. So you see here, a browser, that program there, is a combination of the HTTP protocol client side and an HTML interpreter. So this interpreter is to interpret the HTML page because there are some markups around. Based on the markup, the interpreter will know how to display a web object so that it appears properly and nicely. Now the server, web server. Very few of you guys have experience building your web server, I suppose. Yeah, so in this example we see Apache, I think is still the most used server, but this guy here is catching up, Nginx. Both of these servers are implemented using C and C++ socket. All right. So the web server implements server side of the HTTP protocol. So what it does is to receive requests and send back response. So that's the exact opposite of the client. It's to receive objects and send requests. So let's see the exchange. So this client up here, sending HTTP request and then receiving the HTTP response, and containing the HTTP response is the web object. Similarly, if it's a phone, yeah, Safari sending HTTP request and server sends back an object and Safari renders and displays the object. All right, so that's HTTP, Hypertext Transfer Protocol, HTTP. And HTTP runs on top of this transport layer protocol, TCP. And the whole process is actually this. First, tries to establish a TCP connection between the web server and the web client, and then sends the HTTP messages. So before the client and the server sends HTTP messages, the client and the server sends TCP messages first. So starting from the client, initiating a TCP connection. Now, if this is a web server sitting on the default port, it's going to be port 80. And then server would accept the TCP connection, inform the client, and then client can begin sending the HTTP request. And the server sends back HTTP response. When everything is done, the TCP connection will be closed. Know that HTTP, as you see, very simple, request response. In fact, each of these requests is treated as brand new, it's very fresh. That means what the server is doing there is to not record anything about the client. So there's no information about the past client requests. Okay? And we call this type of a service a stateless service. So on the server side, there's no requirement of storing anything about the client. So this is really nice because the server does not require a lot of memory space for these information. All right? Yeah, protocols that maintain states can be complex. So this is the other extreme. You might need to maintain the past history, which can be long. And you might need to maintain history for multiple clients. How about that? Yeah, that's a lot of burden in terms of a memory space requirement. And besides the service load, the memory requirement, what if the server and client each crash while the other continues to run? Then the states on the two sides might be inconsistent, and they will have to resolve the conflict somehow. That's the worst, right? So should you trust the client or should you trust the server? This is one of the classic car problems, all right? Yeah, so that was HTTP. Can you tell me whether HTTP is client-server based or peer-to-peer? Yeah, type it on the live channel. Oh, by the way, Hassan had a question. HTTP is stateless. How is things like authentication done? And Henderson is replying, there's a certificate which distributed by a third party. And Hassan was responding, yes, HTTP is client-server. So recall, yeah, Henderson, that was called the certificate authority. So nowadays, over the web, if security is an issue, authentication is an issue. By the way, security and authentication are actually two different things. Authentication is to make sure that the website you are contacting are really the website you meant to contact. Sometimes hackers can pretend they are Google, they are Amazon. And if you log into those hijacked websites, then quite a bit of information might, for example, your credit card information might be stolen. So you do care whether the website you go to are authentic. So Hassan was asking, if HTTP is stateless, how do you authenticate the website you're going to? And Henderson is providing an answer. Yes, nowadays, we request a third party for a certificate for a particular website, for example, www.google.com. And when the certificate matches what the website provides to you, when the certificate from the third party, of course, the authenticated third party, higher authority third party, matches the certificate you receive from the website you go to initially, then you establish a authenticated connection. All right, so Hassan, that's the idea. And very good. So recall when we were going through chapter 2.1, what are the very important design elements when you are creating a network application? First, the communication models, right? So this is an example. Web is an example. And HTTP here is using the client-server communication model. And you also heard from the video which protocol it use, what kind of socket it use. Is it TCP or UDP? Yeah, so feel free to type up on the live chat. Let me know from the video. Did you see it creating a TCP socket or UDP socket? TCP, there you go. And in the video, you see that, hey, it will take some time for the TCP connection to establish before the client can start send request message, and then the server replies a response message, right? So there's one round trip and another round trip to complete a web request. Very good. So that's the second design, creating a socket, and you decide. Third design element, the is it TCP or UDP, the kind of QoS requirement. So for web object, it's text-based and it's not really time sensitive, so TCP. So you create a TCP socket. So that's the second. And the fourth design element. The third one is what? Defining the packet format, message format. And you see from the video, there are two kinds of messages. One is the request message. The other is the response message, right? In fact, later today, you will see the format of the request message as well as the response message. Then you get to experience, to enable World Wide Web. Yeah, what are the design choices? Okay, the designer of World Wide Web and HTTP decided to do, made. And now, well, we will talk a little bit more about the communication model. Recall that we establish a TCP connection first, and then we request an object and we close the TCP connection. Okay. If you think about it, this is 2 round trip time. If you want to download 10 objects, then it's what, 20 round trip times. That's quite a bit of delay if we are connecting to a website that's in, for example, in the States or in Africa. So the next topic is called the HTTP connection modes. Okay, HTTP as a protocol over the years has evolved. Okay, and there are 3 varieties of connection modes, and one after another gets more and more efficient. Meaning, the time to get the web response back, the response time gets shorter and shorter. So there are going to be 2 videos. Pay attention to these 2 videos because what's coming up is quiz 9. And I'm going to ask you to calculate the response time for different mode, for different connection mode. All right? Okay, let's start from describing the different connection modes over in the history. Okay, HTTP history. This is 4.5 minutes. HTTP connections. There are actually 3 flavors of HTTP connections: non-persistent HTTP, persistent HTTP, and third, persistent HTTP plus pipelining. All right, so let's start from the most basic, the oldest flavor, non-persistent HTTP. This is implemented in the pioneer versions of HTTP, let me call it that way. In that, you send 1 object per TCP connection. So the clients and the server sets up a TCP connection, and then you send 1 HTTP request, you get 1 web object, and then you close the connection right after that. So to download multiple objects, you need to create multiple connections, one after another, sequentially. Now, in persistent HTTP, the main idea is, well, why do we keep opening TCP connections and closing them? Why don't we just reuse the TCP connection we have started in the first place? So in persistent HTTP, client and server establish the TCP connection, and then first web object exchange, second web object request, and the object response exchange, and so on and so forth. So 1 single connection to send all the objects. All right. Now, the basic persistent HTTP mode works more like that. So you have 1 exchange to establish TCP connection. And then it's just object 1, and object 2, and then object 3. Okay. But the thing is this. When we establish the TCP connection and sending out the first request for object 1, really, before the object 1 is being transmitted back, you see, client over here, it needs only this amount of time to send the request message, right? Client is immediately left idle right after that. So why don't we send the second object's request, the third object's request, and the fourth object's request subsequently and immediately? That way, you just need another exchange like this and, just a few more transmission time. Then we're done with everything. Unlike here, for each object, you need this much time, and the second object will wait this much time, and the third object waits even more time. Okay, so This here is the persistent HTTP plus pipelining. Nowadays, when people say persistent HTTP, the implication is that, hey, it's persistent HTTP with pipelining. And by the way, this is HTTP, the 0.9 version. And persistent HTTP without pipelining, that's the HTTP 1.0 version. And the one with the pipelining is the HTTP 1.1 version. All right. Now let's go through the animation for the very standard non-persistent HTTP protocol's behavior. Let's suppose we are looking for this object here. So the URL contains the host name, the path, and the file name. And let's see that this base file here contains 10 reference objects. So there are 10 images embedded. Step number 1, the TCP establishment. Client here initiates connection request. Server sitting at this location at port 80 will accept the connection and then send back a, sure, open it message. Second exchange is the client sending the request message. All right, so in the message, embedded is the URL. All right, so that's going to go through the socket, and URL right there in the message. Server will receive the message and sees the URL, finds the path, finds the file name, and therefore extracting content and generate the response message. And that response message is shoved again through the socket back to the client. Now, immediately after the response is sent, the server closes the TCP connection. HTTP client here receives the response, parse the HTML file and displays it. And in that process, it's discovered that there are 10 more reference objects to download. And the client then will repeat step 1 to 5 again and again and again, 10 times until all 10 objects are downloaded. All right, now next, let's try to calculate the response time for these 3 different modes. Okay, and the video is almost 4 minutes, but shortly after that, we'll have quiz 9 and we'll exercise calculating response times ourselves. And the time to do that is pretty long. Let's try to count the amount of time to complete the entire download. And we call that the time to download an entire page being the response time. Before calculating it, let's define this term. RTT, which stands for round trip time. It is the time for a small packet goes out to the other end and comes back, out and back. So it's a round trip in a sense. So client over here, server code over here, to initiate a TCP connection, the connection request go, connection established, granted messages come, that's 1 round trip time, right? So 1 round trip time for initiating the TCP connection. And it's another round trip time to send HTTP request and receiving the HTTP response. So this part is 1 round trip time. But the dark, thick square here, this is the time it takes to transmit the file. Okay. So when the object is very small, this is very narrow. When the object is large, this could also be quite wide. So let me fill it up. Yeah. So the object itself could be big. The transmission time can be long. So the shadow part is the file transmission time. So the response time to download just 1 object using non-persistent HTTP is 2 round trip time. 1 here, 2 here, and then the file transmission time. Now we can try to account the response time for that page we were loading, the something.edu, the object there. So we have the base and then 10 more objects. So altogether 11 objects. If we're running the non-persistent HTTP connection, then we have 2 round trip time plus the transmission time for object number 1, the base object. For each of the 10 objects, we do more. Okay, so the transmission time might vary a little bit from object to object, but round trip times remain the same. Right, so there are 10 of these. So 22 round trip time. So 10 of these plus this one over here, the base. And the sum of the TX. Okay, and depending on which object it is for all I. All right. Now, but for persistent
HTTP. Oh, the server is going to leave the connection open after sending response. So subsequent HTTP messages between the client and server will be sent over the open connection. Client can send requests, as I said, right? Persistent HTTP without further clarification, it's the persistent HTTP with pipelining. So the client here will send all the 10 requests as soon as possible. Okay. So in the end, it's just one round trip time plus the transmission time of all these objects. So altogether, just 2 round trip time. First is to establish the connection. Second is to download the first object. Okay. Third is to download all the rest of the 10 objects. So it should be 3 round trip time plus the transmission time required to send all these objects. So 22 versus 3. Big win over here, right? Yeah. So this is in HTTP version 1.1, the most up-to-date version.
All right, now that's exercise. This is quiz number 9. The scenario is this. Let's download a web page that contains 1 base HTML and 3 reference objects. Okay, it's a scaled down version of what we did in the video. So tell us the round trip time. Tell us the response time in terms of RTT, okay? And let's just ignore the transmission time. Let's just ignore all these TXIs. Now tell me, what is the response time if you send using non-persistent HTTP versus using persistent HTTP? This is the one with pipelining, right? By default. And persistent HTTP without pipelining. We have also calculated this mode in the video. Now, this one is the one that we have not yet done any calculation. This is non-persistent HTTP with parallel connections. So after you download the first object, the base HTML, there are 3 objects in the page. So what we do here with the parallel connection capability is that you start 3 parallel connections to fetch all these 3 reference objects simultaneously. All right? So then if we do it that way, after downloading the first base HTML using a non-persistent connection, we download 3 reference objects in parallel, again using the non-persistent HTTP connection mode. All right, so these 4 modes. Let's go to the Discord space. You see that in channel W4 quiz 9, the quiz is already posted. Guys, feel free to type up your derivation. In fact, those who show me the derivation, because then I see the logic behind your calculation, gets the bonus. All right? And you guys have only 5 minutes. All right? 5 minutes. So each cue should take only a little bit more than 1 minute. And let's start counting time. 1 minute left. Guys, hurry up. All right, time's up. But I see you guys get the idea. So team 6 is the first. For each object, you just need to start TCP connection and get it, right? And there are 4 objects and one after another, 8. And persistent connection is always 3, no matter how many reference objects, because you pipeline all the reference objects together in one round trip time, right? And for Q3, then TCP connection to start with, but you keep that TCP connection, get the base, and if there are 3 reference objects and you kind of download them one by one instead of pipelining them, then 3 objects will be 3 RTTs. Okay, so 5 RTTs. Last one, 1 connection and get the first, the base HTML, that's 2 round trip time, right? This is a non-persistent connection, so must establish TCP connection first. And then you get 3 reference objects and you know that this is non-persistent connection. So for each object, yeah, you need to set up in a TCP connection and then fetch the object. But you can run all these 3 connections in parallel. So just what? 2 RTTs to get the 3 reference objects in non-persistent parallel mode. All right, so good. Yeah, very good. And feel free to correct. I guess by now it's very clear how different connection modes work and how you calculate the response time. And we get to move on and talk about the design element number 3 more, defining the messages that you exchange in the protocol. So first, let's talk about the request message. And we'll start by doing this, introducing a simple example of request message, and we'll just go through the message. What's nice about HTTP is that the messages is readable, human readable. It's not like encrypted into 0, 1, 2, 3, A, B, C, D, E, depending on the mode they use to do the representation. So HTTP messages are human readable. And here's an example of the request message, and you will hear Polly introducing how you read a request message in HTTP.
Let's take a closer look at the syntax of HTTP request message. First is the request line. It's only a single line, 3 tokens, separated by 2 spaces, one over here and one over here. First token indicates the command the client is issuing to the server. So get here is the most classic command. Second token here indicates which object the client is wishing to download. So here you see the path and the file name of the object. Third token is very straightforward. It's simply telling the server the version of the HTTP protocol the client is implementing. Now, header lines. Syntax is also quite straightforward. Column in the middle. Before the column, this is called the attribute or the field name. And whatever comes after the column is the value of the attribute or the value of the field name. All right, so User agent is a well-defined attribute in HTTP. It indicates what implementation the browser is and the version of it. So user agent indicating the meaning being user is using a browsing agent called Firefox, and it's version 3.6.10 of Firefox. Okay, similarly, okay, keep alive also a predefined attribute. And the value 115 is saying that let's keep the connection alive for 115 seconds if there are no messages being sent. Connection indicates the type of connection the client is wishing to establish. It's the keep alive kind of connection. And so you see the syntax and a little bit of semantics of HTTP requests.
All right, so that was an example of a request message. Now, more formally, the general format of a request message. But you see from the example, right, there's a what? The header line, and then a bunch, I think the command line, and then a bunch of header lines, and then the end of the message. That's it. Okay, so more general format of the request message.
Next, the general format. Okay, now with that introduction, with a specific example of HTTP request, so this will be slightly easier. You see here, first is the request line. And then we get a whole bunch of these header lines, and it ends with what? CRLF. Okay, in fact, at the end of every line, CRLF. Okay. And in the request line, we have three components: the method, the argument for the method, and the version. Okay. Some comments might not contain the second component. All right. And you see here, for each header line, we see what? Pair of attribute name and value. So in the slide, we see this is the header field name. So those attributes are sometimes also called the fields, the field names. So attribute value, or field name value. Good. So lots of these. Okay. And hey, this is the thing that we did not see in the previous example. Yeah. Occasionally, you do need to have a body in the HTTP request message. And this is what, if you recall, the post command. We're sometimes posting content, posting data onto the server. So those data, those information to be communicated from the client and to be registered at the server will be here in the entity body. So real data generated by the user is here. Okay. So officially, in general form, the HTTP request comes in three parts: request line, header lines, and body. But for most of the HTTP requests, there are just two parts: the request line and the header lines. Now, let me add a little bit more. First, the post method. You've heard me. There are sometimes web pages that you need to fill forms, okay? Input names, usernames, potential passwords. Okay, those input are uploaded to the server in the entity body. There's another way of doing that recently. Okay, it's called the URL method instead of the post method. What you do there is, hey, you could be clicking just buttons, okay, a certain link, in fact. What the browser does there behind the scene is more like this, okay? Requesting to the server, all right, okay, but it's actually sending a phrase like this. Instead of a file name with a path, okay, so instead of having a path, something, and then something.html, so it's a very weird form of HTTP request, okay? While we know this is more classical, but these days we see this more. Animal search question mark, and then something and something. Okay. So this is actually a query. Okay. Unlike request sounds more like requesting for a service, requesting for a file, for an object. But clients often query the server for a service. Okay. For example, look up a database. Exactly. So in a way, the World Wide Web is evolving from a huge hard disk, a global distributed hard disk, to a global distributed database. Okay, so in the HTTP request there, we are actually sending a query. This is the name of the query, and this is the input to the query. So this query obviously contains two arguments in order to execute, for the server to execute. all right? It's using the get method instead of the post method earlier. So this type of a service request is using the get method, but in HTTP request message. And the input is exactly in the URL field in the request line. Okay, and it's this way. Yeah, the query name and then the arguments for the query.
All right, and last video is just to tell a little bit more other methods in addition to post, get, and URL.
And the last slide about HTTP request here is quite straightforward. What it says is to tell you again what are the comments, okay, possible in HTTP request line. In version 1.0, we see get, we see post, we see head again. Okay? But this is all that HTTP 1.0 supports. In HTTP 1.1, we extend the comment options from the 3 classic ones to add 2 more, put and delete. Okay, let's go through these 3 other comments. First, the head comment. So this is usually for a web client to send sort of initial HTTP request to the server, and server will send some response back, but only to tell the status of the server or the specifications of the web server, and leave the actual web object the client is asking for out of the response, so that the response is very short. And what's contained in the response messages are just all the essentials, like, you know, what is the version of the web server program you're running over there? What is your IP address? What is the time date? What is the time date, the object that the client is asking for being modified last? Okay, things like that, the essentials about the server, about the object, so that when the client receives a response like that, the client can plan a little bit better ahead of time how the client does the requesting. Sometimes when the file is really large, the client might try to dissect and then do the requesting slightly differently. And put here, this one is actually quite forward, just to upload the file in the entity body of the HTTP request to the server, right? So in that request, we also specify which path in the server we want to upload this file to. Okay, so it's working pretty much like the FTP. If you recall FileZilla, you are dragging a file to the server, right? So it's uploading a file to a specific path on the server side. So put here implements file upload. Delete, deleting a file. So FileZilla also allow you to do this. So essentially, HTTP 1.1 is to extend the original HTTP to include all the file uploading, downloading services, because the original HTTP only does file downloading, not quite the uploading. Now, when HTTP 1.1 is available, FTP protocol quickly loses its popularity. Okay? And that's why we rarely use FTP these days, because HTTP, the web browsers can do all these for you. All right, so this is HTTP request.
All right, and that takes us to quiz 10. So it's also the time to take a break. So what we're going to do is let Polly introduce quiz 10. All right, and we'll be taking the break while you guys working on quiz 10, because quiz 10 is trivial. All right, so now quiz 10. So what I'm showing here is a HTTP GET message. Yeah, it's a HTTP request essentially, and this is captured by a tool called WinDump. Okay, and as you recall, HTTP messages are all human readable in ASCII code. So you can see, oh, this is what? The request line, right? There are 3 fields: the comment, yeah, the path, and the version of HTTP, and then a bunch of these header lines. Good. So you recognize it's a HTTP request message. So Q1 asks, what is the URL of the document this request is asking for? And why do you think so? Tell why, please. And is this Q2? Is this a persistent, non-persistent or persistent connection mode HTTP? Okay. And how do you tell? How did you tell? So from where in the message you tell? It's say in persistent mode or in the non-persistent mode. All right. Let's go to the Discord space, channel W4, quiz 10. Oh, okay. We have very fast responders. And again, as I said, quiz 10 is trivial, so I'm not surprised. Guys, for this one, you have only 2 minutes to work on. And we'll take the break in the meantime. It's now 11:12. We'll resume and I'll talk about what you guys have there for quiz 10. 11:22. So let's resume 11:22. And feel free to work on quiz 10 and type up your solutions. All right, time to come back to, oopsie, wait a second. There. Okay. Yeah, so quiz 10. It seems quite straightforward, right? As I see, you guys can tell easily. First of all, the URL is gaia.cs.umass.edu/cs453 index.html. And it's a persistent connection because we see, right, in one of the header lines, it says keep alive. Yeah, we are keeping the TCP connection alive, which is the persistent connection mode. All right, all of you get this correctly? Very good, very trivial. And so we can move on. Okay, and what about the response message? Oh, by the way, there was a question during the break from Sam. Can we see an HTTP request message in our computer? Yes, you may with some tools help. Okay, so I'm gonna actually show a demo that you send a request as human beings, but through a tool called Telnet, which is obsolete these days. And I used to enable Telnet so that you can Telnet to somewhere, for example, Gaia. But I just set the firewall up, and you can only Telnet to a server within NTU. Okay, but I'm gonna show in the demo. Okay, coming up. I think that's the next topic, that you can use Telnet to pretend that you are a web browser and send a request message, and you will get a response from a real server. Okay. Good. All right, so let's check out the response message. Again, let's use an example, but response message usually contain data, so you see that this video is going to be longer. And it's about, let's see, it's about 6 minutes. So bear with me. Let's check out the format of the response message.
Now, finally, the HTTP response message. Okay, the second type of messages defined in the HTTP protocol. You see here, generally, 3 parts. First, the status line. Second, the header lines. And the third, the data. So the entity body, so to speak, from here and down. Okay, and these are very similar to the header lines we see in request message. Each line, you see attribute and the value. Attribute and the value. Status line. 1, 2, 3. Again, 3 components. Let's go through each one of them as well in a bit more detail. In status line, first here, familiar. So the version of HTTP the server is implementing is the first component in the status line. Second, this is the status code. Okay. So in HTTP, it defines quite a number of these status codes. Each of these indicate a different condition. Okay. Some more related to the server, some more related to the object being requested. Okay. And for each of these status code, there's a status word being shown as well. That's the third component in the status line. So 200 here indicates okay, meaning the HTTP server is working well and the object you're looking for has been found. And it's going to come here in the body entity. Now, second part, the header lines. We see date. Yep, this is the date, time, the request is being filled, and this response is being generated. The server, this is an Apache server, version 2.0.52. Apache is one of the most commonly used web server implementation. Yeah, I think you heard about the other one, Nginx. So Nginx is certainly rising. Okay, it's not quite yet the most popular one. Well, let me clarify. By popularity, I meant the number of machines running a specific version of web servers. So Apache is still the most used web server. But if you count only the number of downloads recently, it might be Nginx. That's why you see I say that it's actually rising. So I think maybe in just a couple months, there will be more Nginx server than Apache servers. Last modified. Yeah, so this is to indicate when is the object you're downloading last modified. Oh, okay, it's a really long time ago. All right, e-tag. What is this? This is actually, hey, for each version, okay, of the object that you are downloading, there comes also with a version number. So e-tag there is to indicate a version number. Nowadays, as you see, the HTTP protocol is not used only for downloading purpose. It can also be used for uploading. If there are multiple users there using different web browsers trying to upload the file, for example, poly and Caleb, the TA, tries to upload and override the grades Excel file, then you might have a consistency problem there. So the number here is to break tie, to make sure that a newer version does not override an older version or something like that, to resolve conflicts, so to speak. And accept range. Yeah, yep. So, you know what? Earlier when I mentioned the head comment in the HTTP request message, right? So when you send such a comment in the HTTP request message, the server responds with only the status line with the header lines, but without the data. Okay, so server there can actually tell the client, you know what? I'm a server that allows you to request content in terms of bytes. So the client there seeing this can then send the request more officially instead of using the head command, using the real get command and request to download byte 0 to maybe 1023 or byte 0 to byte 100. Okay, so you could do a range request in a way. And the server's next header line, content length. This is to indicate the size of the file or the size of the object that you're downloading. So you see the file size of the object is one critical parameter. Okay? If you're implementing a web server, you need to know a way to find out what the file size is or the object size is. Okay, the size is a bit messy. Let me clear the markups. Keep alive. Oh, good. This web server implements persistent connection. Okay, and so it indicates timeout interval is 10 and maximum 10 requests. So this is a persistent connection, but in the connection, it only accepts up to 100 requests. All right, so if it's more than 100, then you will force close. The server will force close the connection. So connection, keep alive. Content type. Yeah, just like the client size header line we see. Yeah, the client accepts content of a certain format. Here, okay, this is to indicate the object the client is asking for, which format it is. And we see this is text-based HTML file and it's coded in ISO ep8. Right? And empty line, indicating this is the end of the header lines. Right after the empty line, the data goes here. If it's an HTML file, then hey, text starting from here. Okay, the first file. So this is an example of HTTP response message. You see the structure is very much like the HTTP request messages.
Yeah, so structure very much like the request message, but the variety of the header lines is a lot higher. Okay, so you heard something called last modified since. We're going to see that header line in a mechanism in HTTP called the local cache. And the last video is just to show a few more status lines, status codes. You'll see that the famous 404 not found.
Next is just to share a bit more. HTTP response messages status code. We've seen earlier in the example 200 OK. This is saying request is successful, object is already embedded. 301, that means the server is saying the object is moved to a new location specified later in this message. So sometimes when you run into a message like this, you see, oh, click here. That's going to take you somewhere else. It's a redirecting link. If you see status code 400, that means your HTTP request format is not quite correct. Bad request. 404, that means the object you are asking for is not found. 505, HTTP version not supported. So in case you're using a very old browser, or if you're contacting a server that's very old, and yet your browser is implementing something newer, then you might not be able to communicate. The server is going to tell you this. Sorry, 505.
And that takes us to quiz 11. All right. Yeah, there's a question from Henderson. Henderson, I'll come back to your question a little bit later. Let's go over quiz 11. This one is also straightforward. So this is, oopsie. Let's go to the whiteboard. And this is quiz 11. And you know what? This is an HTTP reply or an HTTP response message. So you see the status line, the 200 OK status. And then, this is header line date. Header line, the gerund of the server. Header line, last modified. And so on and so forth. And then this is what? The break between the header lines and the real data. Good. Now you see. Q1 ask, was the document found successfully? Okay, and hey, guys, pay attention. I did not ask for why, so you just need to tell me whether the document is found. And how many bytes are there in the document? Q3, what are the first 5 characters of the doc, okay, being returned? All right, so that's quiz 11. Let's go to the Discord space and channel W4, quiz 11. Yeah, I see. Very fast. So you guys must be following the lectures really closely. Yes, for 200. Okay, so guys, no thinking time. Just go ahead and type the answer because this one is really straightforward. Okay. Yeah, because we see 200 OK, right? That's the status code indicating that, yes, the request has found the response. And in the content length, you see the size is 3874. And the first 5 characters of the doc are what? The smaller than sign, okay, the exclamation sign, and then DOC. Very good. So let's just check. Team 6 check. Team 7 check. Team 9 check. Team 1 check. And Team 19 check. Team 1 again check. Team 2 check. Team 5 check. 15 check. Yeah, James, thank you. Yeah, using Wireshark also tell you the content of the packet. Team 21 check. Yeah, I see many of you are typing your solutions up. But, okay, check these real quick. All right, Team 12, Team 10, and Team Brian is Team 8. Okay, Team 8 check. Brian, I would appreciate if you, great, thank you. All right, and I see Shi-En and Kelvin also typing up. Yeah, so take your time. So let's come to the live chat and then check out the question from Henderson in the meantime. On the timeout part, does it mean that if the connection is not used in like 10 milliseconds, the TCP connection is forced to be closed? You know what? The timeout max is 100. Yeah, that means after, I'm not quite sure what the unit is. Yeah. It can be 100 seconds, could be 100 milliseconds. So the timeout, okay, keep alive timeout, meant wait for that time. If there are no longer requests and response messages going through the connection, we close the connection. Yes. Okay, so you keep it alive for that long. So Henderson, you're correct. And good news, we now come to demo. Sending HTTP request and get a HTTP response from a real server. All right. That explanation gave you a doubt. Hey, tell me, Luis, what is the doubt? So while you're elaborating, Luis, let me start introducing the demo. So the first video is to explain, to prepare you guys what I'm gonna do.
So what I will show you in the demo coming next is to do this. Telnet to the favorite web server here, and we're gonna use this machine here that the textbook author has set up for us. So we'll telnet to gaia.cs.umass.edu at port 80. Okay, what it does is to open the TCP connection to port 80 where there's a server already running, a web server already running. And anything typed in will be sent to port 80 at this guy. Okay. So Telnet is a remote logging application, just like SSH or RSH if you know what it is. It's another remote logging command for native Unix users. All right, so Telnet is very, very old. Many operating systems probably doesn't support it anymore, but I've already installed it on my Mac, so we're going to show that in a little bit. Now, once we Telnet to the web server, and we'll type up some things. Okay, let's try typing this. Get path name and file name as the argument for the get command, and then the version of the web browser. So we'll be pretending that the Telnet here is a HTTP 1.1 client. And host gaia.cs.umass.edu. All right, so header line. So essentially, we are trying to do a human web browser, okay, by typing online right here an HTTP request message. So once we are done with this, we hit return. Okay, and then we hit return again. Needs to have a what? A \r\n here in order to complete the HTTP request. All right, so the whole thing is going to be like this. And yeah, we'll see what pops up in return, what the server there at umass.edu sends back. Okay, let's not sniff the traffic. Let's just look at the response coming out of the Telnet program. Alright, so let's switch to the demo mode. Alright, let's telnet to gaia.cs.umass.edu at port 80. Alright, connect it to gaia.cs.umass.edu. Now let's pretend to be a web browser. Get. Oh wow, that's pretty long. The path and file, pretty long. Let's copy it from the sides. And over here and print. All right. And then host poly.ntu.edu. How about that? All right. And one more empty line to indicate this is the end of the header lines. There we go. Wow, it's returning a lot of things. Scroll back, and scroll back. Wow, very long in fact. But it looks like it's an HTML file, right? It's an HTML file. Now, this is a hyperlink to an text HTML file. Okay, let me scroll a bit faster. I don't know how long this is. Oh, there we are. Yeah, so we typed up this line here, okay, and we also say we are host poly.ntu.edu.tw, and an empty line, and then return again. The whole message gets out to the web server at gaia.cs.umass.edu, and the web server returns this HTTP/11 to the 200, okay, and header lines number 1, the date. Header line number 2, the server. Oh, it's an Apache server. X power by PHP, I see. Content length, content types. And hey, empty line to indicate this is the end of the header lines. And starting from here, the real body. Okay. So we get the output of calling this PHP query at this path. Let's see, interactive problems, computer networking, a top-down approach. Oh, okay. So this looks like the main page of all these interactive exercises that we see every now and then on the slides. All right. So there, essentially very text-based interaction between the client and the server. As human beings, we could also do it right here, right now, online as a web browser. All right. And I think, let me just go back a little bit here. You see here, 200 is a very classic example of, hey, the syntax defined in an application layer protocol. In HTTP, to be exact, 200 is to indicate OK. So OK here is just to say it explicitly, the semantic of 200. Right? So that concludes the messages format, semantics, and syntax of HTTP.
All right, good. So that was the demo. You see that you can use this program telnet. And I think James suggested using Wireshark. That's a packet sniffer, much like the WinDump utility program I mentioned in quiz 10 and 11. So these tools will all allow you to see the content of the request response messages if this is plain HTTP, not HTTPS. The secure version of HTTP then encrypt the content, then you probably don't see much of the content. I think you still see the status line, you still see the request line. I think you see also the header lines, but not quite the content. All right, so there was a couple questions. First, the easier one to answer is that Brian and Yucheng are trying to connect to the PA server. I guess you guys want to try out the telnet program. Sorry, I just disconnected it because I see some activities. I guess they're coming from you. But you see that I don't see you guys logging in while there's a connection. So I thought that the activity is a little bit suspicious. So I just pulled the network cable. But after the lecture, I'll connect them back up, all right? And the earlier question was, as I was answering Henderson's question about if we wait for some time after the keep alive timeout, Henderson there using a 10 millisecond as an example. I think Henderson meant that if this is a keep alive connection or persistent connection that waits only for 10 milliseconds. If we wait up to 10 milliseconds and there's no data, then we close the connection. And Luis is confused, okay, because in quiz 10 and 11, we wait for 100 milliseconds. So if the keep alive duration is 100 milliseconds, yes, we close the connection after wait for 100 milliseconds and there's no data, okay? I guess that's the issue here. If the keep alive duration is 100 milliseconds, but we close the connection only after 10 milliseconds, then that persistent connection might not be effective, reducing the amount of round trip times we need to spend there, right? Because TCP connection is created and shortly terminated. Created, but shortly terminated, 10 milliseconds. So if the keep alive says 100 milliseconds, we'll keep it for at least 100 milliseconds. Only when during this 100 milliseconds, there's no data, no request, no response at all, then we close it. Okay. I hope it's more clear, Luis. And Henderson, I think you meant like 10 milliseconds, you meant a keep alive connection that sets the keep alive duration to 10 milliseconds, right? Okay. Yeah. Yeah, sorry, Brian and Yucheng. Yeah, so I'm trying to be careful maintaining the PA server because hackers are very active these days. And I've seen some suspicious behavior earlier. They could be just probing. So these are unfamiliar IP addresses. But as I see, you guys are trying to connect from within NTU, but I don't see a particular legitimate users logging in. So it looks weird. It looks like someone within NTU tries to guess the password of somebody in the class. So so I pull the cable. All right. I'll try to connect them back and see if it works for you. Yeah. All right, so let's move on to the next topic. It's called the cookie. I think many of you are aware of cookies. And some of you probably regularly clear the cookies you have in your browser. So the first video explains the mechanism and what is useful. It's something that's a little bit more convenient. If you recall HTTP being stateless, right, in one of the earlier videos, that means the server does not maintain any information about the client. But you see that a lot of these shopping, e-commerce websites, it would be nice if they keep the customer information around so they can infer and provide sort of intelligent recommendations of the products the clients might be looking for. Okay, so cookie is in a way to make HTTP stateful and for certain applications, for certain websites. So here's the mechanism.
Next, cookies. Yeah, many websites these days will try to prompt you to set up cookies before they allow you to visit the website further. So it's very, very relevant to our everyday life. Let's see how it works. Okay. First thing is, the cookie setup process is always initiated from the website. So meaning from the web server that your web browser is requesting objects from. So web server there is going to send a message to the web browser carrying a special header line. Okay, it's the cookie setup special line. And the web browser there, upon receiving such a message, it's going to generate, okay, a corresponding message if you click OK to insert cookie. And that message is going to carry, again, a special header line saying cookie OK. All right, so exchange of messages between cookie setter and cookie allower. Now, when you say, OK, I will allow setting up the cookie, your browser is going to add an entry to the special cookie file on your local disk. Okay. So that is exactly what's expressed here in the special cookie setup line. And when the server receives the message allowing cookies, server would then add a special entry as well to the backend database. And that entry set up here and here will actually map to each other, allowing the server to identify who you are and when have you visited the website last time. Okay. Let's use an example to explain. It will work slightly better. Let's say Susan always accesses internet from her PC. And she's visiting a specific e-commerce site the first time. In the initial HTTP request, okay, that arriving at the server, the site will then create a unique ID, okay, and that will be an entry being added to the backend database. Right? So that ID is going to be carried. Okay, in the message, the site sends back to Susan. So that's going to be set cookie and then the number created here. All right. So local hard disk you have there, or Susan has there, will have that entry, okay, set up in the cookie file. So this will go back to the server, okay, carrying also that special ID that Susan has already allowed to set up. And then at this point in time, the server would finally enter the entry to the backend database. So that's the way it works. Let me illustrate, okay, and so that you know clearly what's going on. Client, server, or Susan, Amazon.com. Okay. Now, at the client side, you have this special cookie file, and it's managed by the web browser. And you might have clicked OK to eBay. So eBay has already set up a cookie entry carrying unique ID ep8. Server here has a local disk as well. It's maintained more as a backend database instead of just a simple file. Right? So, but when you visit the website, Amazon.com the first time, you send an HTTP request message. Now, of course, you have not yet been in Amazon before, so there's no entry for the Amazon website. Okay, so in your initial HTTP request message, there's not going to be any cookie special header lines. All right. So when Amazon.com here receives HTTP request, of course, it will try to grab the objects that you're looking for and try to generate the HTTP response with it. But in the meantime, it will be creating an ID, okay, for this particular user, okay, and add that to the database. And in the response, it carries the web object that you're looking for, but it also carries the special header line, the set cookie line. Okay? And hey, see the ID created is carried over through the HTTP response message back to the user. So web browser here sets up one extra entry saying, hey, for Amazon, the website, use ID 1678. So for the subsequent visit, subsequent browsing, all the HTTP request messages is going to carry the cookie OK and I am a user 167A header line, right? So here the server, of course, will be generating the web objects, generating the HTTP response message that you're requesting with the request message. So response message. But the response message might also contain additional content, okay? Server there could be seeing your browsing history a couple clicks back and discover that, hey, you might be looking for a specific item, okay? And then recommend potentially items you'll be interested, okay? So that might also be part of the response messages. So showing the items you are looking into buying as well as related products. Okay, so for example, if you're looking to purchase a phone, then the website might be recommending a phone case, okay, or a number of phone cases. So what's amazing there is 1 week later, okay, when you come back and try to purchase something from Amazon again, okay, the first request message you'll be sending will already be carrying the cookie entry. Okay, so once you have it set up locally on your cache file, on your cookie file, for all the subsequent HTTP requests, it's going to by default carrying the cookies. Amazon here will know, yeah. So over time, the server will know probably your profession, probably your income level, things like that. Okay, so that's why it gives people a certain creep about setting up cookies, and you might be warned, be careful about setting up cookies there.
All right, so from the video, you see that there are a couple newer header lines like set cookie and cookie, and those are used for setting the cookies. Next video about cookies to talk about the nice things about using cookie and the not so nice things about using cookies. And you hear Polly saying it at the end of the video. It's nice for the e-commerce websites tracking the clients. Okay? And sometimes it will save you some time typing up passwords again and again as well. But on the downside, it allows the websites to track what you do there. And over time, some of you might find this a bit freaky. Okay, so let's talk about the trade-off and the potential issues maintaining cookie consistency.
Now let's discuss cookies a bit more. We're going to talk about the trade-offs of using cookies. First, the cookies from a business perspective, from a website's perspective, is actually quite convenient. So you see, you can authorize the users quite easily, okay, by looking at the ID in the cookie header line. Tracking the shopping carts as long as the ID is the same, right? This is items purchased from the same user. You can recommend items so that the users will go, wow, cool, that is exactly what I was looking for next, right? If the user is purchasing a phone and the website suggests purchasing of a phone case. Yeah, and browsing emails, yeah, you will not want to try to log in and type up password again and again. You want to be able to maintain that email reading session, email sending session over time and log in just once. How? Very nicely through the cookie line in the HTTP request. Okay, quite convenient. Okay, otherwise, you guys, including Polly, when I read my Gmail, I have to log in again and again and again. There's no way we could live like that. Right? So convenience. But on the downside, those websites would be able to learn a lot about you. Okay? So you store emails, that's pretty much your personal life. You store your purchases there, that's pretty much also your personal life. Okay? So over a long time, you can imagine Google, Amazon, Facebook, all these major websites, they know a hell of a lot about you. That's why people are freaked out so much about these big sites, okay? Allowing them to set up cookies, allowing them to store information about you, okay? So downside, privacy, okay? Now, another perspective is more technical, keeping states. Now you see, hey, there's ID on the local cookie file. There's ID stored at the server side, the backend database. So server and clients are now storing states of each other, about each other. But some of you might go, hey, wait a minute. Didn't we talk about HTTP being a stateless protocol? And what's nice about stateless protocol is that, hey, none of the endpoints need to store anything about each other. Okay, no storage requirement, and you don't have this problem where, hey, if the connection between the client and server is broken, and you might have these inconsistencies in the states they maintain for each other, right? You have to reconcile and resolve conflicts. And that is actually a very, very hard problem, okay? Who do you trust more, the server or the client? Okay, sometimes it's a bit hard to say, okay? So cookies here you're seeing is, in a way, a hacking HTTP such that we can maintain states, because HTTP was not designed in the first place to maintain states. But then now with the cookies, we have this issue potentially between the client's cookie file and the server's backend database. What if, the entry is inconsistent? Then you might have an issue as well. So trade-off in terms of usage, okay, in terms of privacy concern. Trade-off in terms of technical difficulties maintaining the states.
All right, so that was cookie. Good and bad. Use them carefully. Now, the next two topics, they are called local cache and web cache. So these, by cache, actually what we meant is a temporary copy of the web pages that you have previously visited. Okay, so local cache is to keep this web page locally on the client, and web cache is to keep these pages not exactly on the client, but somewhere close to the client. All right. So both of these caches are there to avoid the client needing to request the web pages from the original server again and again, because that is longer delay typically, and that is generating more traffic to the internet and adding the load to the web server as well. So these two kinds of caches there are to shorten the response time, to lower the traffic load, to also lower the server load. And let's start from the local cache because it's quite straightforward and it uses the if modified since header line.
The next two topics are more about trying to reduce traffic between the server and the client, or trying to reduce the delay downloading a certain object. It's called the caching. So what cache means is to store a temporary copy of certain data. Okay. So conditional get here is like to have a local cache of the web pages that we have downloaded previously. Okay. So the goal is to not send the object again and again and again if the copy we're storing here is already the latest. Okay. Because as a result, we don't need to send the object, and that reduces the delay, and we also reduce the bandwidth requirement. Okay. And so saving the bandwidth is going to be good for everybody. So the way it works is this. Okay. So the first time the client downloads a web page, it's going to keep the copy of the web page on a local cache. So that's somewhere in your local disk. And in the meantime, we record the date, okay, the cache copy is downloaded. And so that when we send a request for the same page again, we carry this special line in the header field, the if modified since, and then the date, okay, of the cached copy, the day we have requested the copy the first time. And then at the receiver side, at the server side, the response will contain the no object if the cached copy is actually the most up-to-date, meaning if the copy at the server has not been changed after the date, then there's really no need to send it again back to the client, okay, because the copy right here is already the latest. So in that case, a special HTTP response message is going to be sent, and the status line is going to read like this. Yeah, 304 not modified. And in the body of the HTTP response message, it's going to be empty. Okay, so no need to send the object. And the way it works is more like this. Let me illustrate. The second time, the client here requesting for the web object sends request message and having this in the header line. If modified since the date the page was downloaded the previous time. And if the server finds that no, it's not yet modified, then send back a short HTTP response carrying the status line. And that's all. No data here. But otherwise, if the object is modified, then we send back a regular HTTP response that says 200 OK in the status line and the web object, the web page again, okay, in the body and the T.
All right, so from that video, there's a very important point. You see that keeping a copy of the web pages you've previously visited locally is nice, because if you need it again, it's local. But what if the original copy at the server has been modified? The copy you have kept locally was the copy that was earlier, before modification. So you want to make sure that the cache version is consistent with the original, with the web page now. So there's this if modify since header line allowing you to query the server whether there's any change. If no, then happy and okay to use the cached copy. All right. So now we enter the last topic for the HTTP chapter 2.2. It's to keep caches also close to the clients, but not exactly on the client. And we are creating a proxy server in a way. So think of it this way: client here, original server here, whoops, original server here, and we create a proxy server somewhere close to the client, okay, and not exactly and far away from the server. That will reduce some traffic from the proxy server to the original server and reduce also some delay. And so essentially we keep the temporary copies on this proxy server. And the proxy server can potentially serve a group of users where they share, when the users share common interests of the web pages on the internet. Okay, so that's the web cache. So the first video introduces the mechanism, which I just briefed, okay, in the last minute.
Web caches. The purpose is very much like the local caches, but the way it works is somewhat different, but not much different though. Okay. The main difference is this: in local caching, we keep a copy of the object here, okay? But now we keep a copy of the object here in the web cache, or also known as the proxy server. Web cache or proxy server. Okay. And in conditional get, we still need to send HTTP requests to the original server. It's just that the original server decides whether to send the object with it or not in the response. Okay, sometimes yes, sometimes no. So we save a little bit delay and bandwidth this way. But in web caches, the goal is actually trying to satisfy some client request such that there's no involvement of the original server required. Okay, so some of the clients doesn't need to reach the original server to get the object. And this is done by keeping a copy of the object somewhere in the middle at the proxy server. Okay, so the way it works is this. Users will set the browser such that for all web access, let's go through the web cache. So subsequently, the browsers will send all HTTP requests to the web cache. So send it to the web cache. If the object, the page we're looking for, is already in the cache, proxy server sends the object back. So you see, it works somewhat like a server, but it's not the original server. It's somewhat a delegate of the original server having a copy here. Okay, so object in the cache, cache return objects. Otherwise, the cache here, the web cache here, would request, okay, from the server a copy of the object. So this request will be like, the proxy server here behaving like a client, okay, of the original server. Web cache there, request object from the original server, like a client. Okay, and after the object is downloaded here, the proxy server then sends the object back to the requester. So let me illustrate. If the object is not here, request go to the original server, response comes back, store a copy, and then forward it back to the client. And what's nice about this is, look at this client down below. If the client is requesting the same object, it's a hit here at the cache. Server here sends back the object directly without going through this segment of the internet. So, cache there. acts both like a client and a server. As a server, so that it served the original client, the objects. As a server, because if there's a miss, it will be requesting the original server for a copy of the object. Right? So some of you might see already, right? A web cache like that is actually preferred by the ISPs, okay, which serves a whole bunch of customers locally. Usually people sitting close to each other tend to prefer fetching or tend to fetch similar content. Okay? So a lot of times ISPs might encourage you to set a web cache, okay, on your browser. Now let's go through a few examples to detail, okay, why using web caching. Local cache, nice, reduce delay, reduce bandwidth. Through this set of example, let me take you through what is the benefit of doing web caching. In a nutshell, a lot more delay and a lot more bandwidth saving.
All right, so that's a general idea of web cache. In a nutshell, you set up a proxy server midway between the client and the original server. All right, so let me use an example, a scenario that is a little bit more general, and let's walk through that, then you will see the benefit of doing web cache. It reduces time, it reduces bandwidth consumption, it reduces server load, while the cost is not so high because there are other ways to reduce delay. So let's start from the first scenario. So this is the basic setup, and let's assume that there's a bottleneck between the client and the original server, and that's creating a long delay. So the first video, there are going to be 3 videos in the series to go through. In the first video, we just set up the scenario where you might experience a long delay because of the bottleneck link.
Good. The example. Setting is this. Servers up here, client down here. So they're part of the institutional network here. And the servers are connected to the public internet. And the internet connects to the institutional network through an access link. Let's assume that the clients here are browsing the web, requesting objects down from the server. The average object size being 100 kilobits, and the average request rate being 15 objects per second. Then multiply the two, you get the average bit rate, okay, coming down this way, right? And that is 1.5 megabits per second. Now let's see. Round-trip delay from the institutional router to any of the origin servers and back. That's set up to 2 seconds. And the access links rate 1.54 megabits per second. And the local area network link rate 1 megabits per second. Now with these, we will be able to calculate the local area network's utilization. 1.5 meg divided by 1 gig, that's 0.15%. But here, 1.5 meg divided by 1.54 meg, that's very close to 99%. And that is a problem if you recall. There's this component called queuing delay in the internet nodal delay. For transmission over a hop, there are 4 components: processing delay, queuing delay, transmission delay, and propagation delay. And the queuing delay is very sensitive to the utilization on the link here. Right? So let me take you here. Queuing delay. Just in case you kind of forget about it. It's very case dependent, and the determining factor is the utilization, which we call back then when we were talking about internet delay, the traffic intensity. So this is the amount of input, and this is the output capacity. You see, utilization again. When this is very small, queuing delay also very small. But as it approaches 1, delay becomes large. When it exceeds 1, delay is actually approaching infinity up here. All right? So close to 1, close to 100% delay, just very long. Okay. Let's come back here. Therefore, if we want to calculate the total delay of web request and object download, it will be round-trip delay here, plus round-trip delay here, plus round-trip delay here. 3 components: internet delay, access delay, and LAN delay. Internet delay, we already defined it. Just make it simple. Just say that it's only 2 seconds. But hey, here, fully utilized link with high queuing delay, it's going to be very long. Let's just say that it takes minutes. It could be even higher. And the access the lane access delay. Now this is very low because utilization is super low. So let's say microseconds, right? So 3 components, which one dominates? Yep, queuing delay on the access link dominates. So bottleneck where? Here, in terms of delay performance. How do we fix this? Let's look at the second scenario.
All right, and we don't have time this week to go through the second and the third scenario. The second scenario is essentially to expand the bottleneck link capacity, because that way then we reduce the queuing delay. Then the overall response time will drop from minutes back to seconds or milliseconds. Okay, so that's scenario 2 in a nutshell. And scenario 3, guess what? It is to introduce a web cache instead of expanding the bottleneck link, because usually expanding the bottleneck links involve digging some roads up and changes the older narrower capacity cables to higher bandwidth cables. So that's very costly. But if you just install a machine, a server, a web cache, it allows you to get to a very high performance, significantly lower response time, and yet it doesn't cost much. Just set up a machine and connect to somewhere close to a subnet. All right, so that's the general idea, but we'll go through scenario 2 and 3 videos next week. All right, and yeah, there was a question from Henderson asking close far. What do I mean by that? Is I usually meant that by close being someone a node closer in terms of delay. A node's delay is shorter. Okay, wait, how do I say that? The delay to a node is shorter. Okay, by far away I meant the delay to that node that's far away is longer. Okay, good. And guys, with that said, I say goodbye. And by the way, Team 5, the PA server is back on. Enjoy. All right. And hey, here's the cue. Goodbye, guys. Well done with the quizzes this week. Okay, bye. Bye-bye. Sorry, poly is not purchasable. That's an interesting idea, however. No worries, yeah. We know it's definitely auto-correction. All right, that's all. Bye.